Okay, at this point, we're ready to look at the controls of temperature and climate. Why is it hot here and cold there? Well, there are some basic underlying rules that control the distribution of climates, and it's probably a good idea to be a rule follower. All right, so what are the rules? Well, what is it that controls temperature? Well, how does latitude control temperature? How does altitude control temperature? How does the unequal heating of land and water control temperature? How do ocean currents influence temperatures? How does the amount of cloud cover and the prevailing winds, how do they contribute to temperature differences? Well, the most important factor in controlling temperature distributions is latitude. And you knew this coming into the class. You knew that it was hotter at the equator and it was colder at the poles. But did you know why? It's because of sun angle. When you're in the low latitude locations, low latitudes, low numbers, that means close to the equator. When you're in a low latitude location, you get higher sun angles, so a lot of heat is generated up. Whereas when you're higher in latitude, I have a couple examples here, 45 degrees in latitude, and here over 60 up to the North Pole. Notice that the sun comes in at a lower angle, spreads the radiation over a greater surface area, so heating is not as great. Whereas when you have the high sun angle and day in and day out for the entire year, the equator would have the highest possible sun angles. When you have the low sun angles, less heat is generated. When the high sun angles, more heat is generated. All right, so the polar areas are coldest because they receive low angle sunbeam. Well, that's pretty easy to see. We'll take a look at a couple of weather stations here. And if you look at the January through December monthly average temperature plots for San Antonio and Winnipeg, well, who has the higher numbers? Well, San Antonio, further to the south, closer to the equator, so it has warmer temperatures throughout. So the higher latitude climates, that's Winnipeg is at a higher latitude, are going to be colder than lower latitude climates, which will be warmer. But there's something else. High latitude climates also have greater annual temperature ranges, whereas low latitude climates have smaller annual temperature ranges. All right, now notice I didn't say annual temperature. I said annual temperature range. There's a big difference. If I ask the question, where's the annual temperature greater? You might tell me the equator. But if I'm asking, where's the annual temperature range the highest? Well, that would be in the higher latitude location. The higher you are in latitude, the greater your annual temperature range. All right, well, what's the annual temperature range? That's the difference between summer and winter. Usually it's the difference between your average January temperature and your average July temperature. Okay, you subtract the January from the July, that's your range. Well, a place like Winnipeg has a big difference between summer and winter. San Antonio has less of a difference. It still has seasonality, but it's a little less of a difference than Winnipeg, being higher in latitude, has a big difference. Another important control on temperature is the degree of continentality, or whether or not a weather station has a maritime location. So let's compare and contrast these. One of the rules is that land heats up faster and obtains a hotter temperature than does water bodies. Now, the reasoning for this, a lot of this is beyond Geography 1010, but to be able to visualize it and remember it, compare sunshine beating down on the land surface and the water surface equally. Well, over land, you don't have any penetration of the sun's rays to any depth, and water a little bit more so to disperse that. Also, the chemical properties of what land materials are made out of versus what water is. Water has a high specific heat. You have to add a lot of heat to it to raise its temperature. Not so the stuff that land is made out of. So when the sun's beating down on both the land and water equally, the land is going to heat up faster. And to a lesser extent, well, the mixing, you get these little currents and eddies that are starting in the water, and it redistributes the heat. Now, there's land, no mixing unless there's an earthquake. Now, here's an important part of this, is the evaporation part of it. Now, over water, you have a lot of evaporation. Over land, you have, well, you still have some evaporation off surfaces, obviously, but you have less. There's less water. Well, when the sun's coming up and beating down on both of them, a lot of the sun's energy is being used to evaporate water, to get water to go from its liquid form to its gaseous form. Whereas over land, the sun's energy is pretty much being used to just raise the surface temperature. Now, for that explanation, it's beyond Geography 1010. I talk about this in meteorology, that it's a significant amount of energy that's absorbed through evaporation. Sometimes we say that evaporation is a cooling process. You know, how we keep cool in the summertime, we sweat, and that sweat evaporates off of our skin. That evaporation requires energy or takes away energy from our skin, makes us feel cooler. Well, another way to visualize the difference between the two, in that if we said that it took 100 units to go from the ice point to the boiling point, if that were 100 units, what would it take to get liquid water to jump its phase and zip around in the atmosphere? Well, if it's 100 to get it from freezing to boiling, it takes nearly 600 to get it to jump its phase and zip around in the atmosphere. Okay, so there, when the sun's beating down, well, a lot of energy is being used to evaporate water, and over the land, well, the sun's energy is directly increasing the surface temperature. All right, so land heats up faster and obtains a hotter temperature. Land also cools off faster as well. All right, so at this point, we're ready to take a look at comparing three different places across the United States. Point A is on the west coast, point B is in the middle of the continent, point C is on the east coast, and I have a graph here for San Francisco, Wichita, and Norfolk. That's pretty close. Well, which one of them would have the greatest annual temperature range? Which one would have the smallest annual temperature range? Well, let's take a look at their annual temperature curves here. Let's see, the blue line is San Francisco. San Francisco's line is pretty flat. It doesn't increase all that much in summer, as opposed to Wichita, Kansas, being in the interior of the continent. Well, there's a big difference between January and July. Okay. All right. Well, why is that? Well, because water heats up more slowly. In the summertime, San Francisco is getting its weather from the Pacific Ocean, so temperatures are only rising gradually. Whereas uh, Wichita is in the middle of the continent, and uh, it's obtaining a high temperature in the summertime. What about in the wintertime? Well, land cools off faster, water cools off slower, and so in the wintertime, San Francisco being on the coast, the water hasn't cooled down all that much, so it's a source of warmth. So the wintertime temperatures aren't as cold, whereas Wichita, green line, it's quite cold in the wintertime because the land surface has cooled off. All right, so it's pretty easy to see that point B is going to be much more continental in climate than point A is. And it's borne out by this graph. But what about point C, Norfolk? Why does it have a temperature curve very similar to the continental one? I mean, Norfolk is near the coast. Shouldn't it have a flattened curve like San Francisco? Well, not necessarily here. And in the case of Norfolk, Norfolk has a continental climate, and it has to do with the prevailing weather direction. As we'll see a few slides from here, here in the middle latitudes, weather basically goes from west to east. All right. Now, of course, you can have the wind direction from any direction on any given day, but averaged out, it's more or less west to east. So in the wintertime, San Francisco is getting its weather from the ocean, and in the summertime, Norfolk is getting its weather from the continental interior, which is hot. Where's Norfolk getting its weather from in the wintertime? The continental interior, which is cold. So Norfolk's temperature line, it's not as extreme as Wichita's, because this is on a coast, and that equalizes temperatures a bit, but it has a temperature curve that's continental. You'd say Norfolk, Virginia has a continental type climate. And here's a Canadian example. Vancouver, which is on the coast, a relatively mild portion of Canada. They say that Vancouver is kind of like the Sun Belt of Canada. Canada has mostly cold climates, but there it's a little milder. It's on the coast. It faces the Pacific. There the winters aren't nearly as cold as they are in the continental interior in Winnipeg. In Winnipeg, there's a huge difference in annual temperature range because winters are so very cold. They're on the same degree of latitude, but where they are in relation to the coast or in the interior of the continent explains the temperature contrast. Winnipeg has a much greater annual temperature range. Okay, so that's a few more rules. The next rule we can take a look at is altitude. Uh, Earlier we looked at how the sun warms the ground and the ground warms the air above it, and it gets colder as you go up. Okay, we looked at this lapse rate diagram within the troposphere. Well, that's because you're getting away from the warmth of the long wave heat of the Earth's surface, and also you're getting away from where the denser air is. As you go up higher into the atmosphere, the air is thinner. It has less mass to even absorb the heat energy. All right, so it gets colder as you go up in elevation. All right, so mountains can have snow-capped peaks. It goes down on average about 6.5 degrees Celsius for every kilometer in height. That's what's known as the lapse rate. In world geography, especially when we look in Latin America, we talk about this altitudinal zonation. There's an altitudinal zonation of climate, of natural vegetation, agricultural type, as you go inland and upland through the mountains. At first, at the lower elevations, that's the Tierra Caliente, which means the hot lands, tropical rainforest. What can you grow there? Well, tropical rainforest crops, bananas, sugarcane, and so forth. And as you get up in elevation, it's more temperate. It's cooler, and so that's where coffee, corn, wheat, middle latitude climates, even near the equator, can be grown in the template. And then up at higher altitude, you have more cold resistant crops like barley and potatoes. Potatoes can take a colder environment. Then above that, you really can't grow crops. It's too cold. But you could graze sheep and llama. And then above that is a very important natural resource, and that's snow and ice, because for the meltwater and for the water resource, you want to have that snow up there as well. Well, overall, as you go up in elevation, you become cooler and cooler in your climatic zone. Okay, well, speaking of the lapse rate, I have to introduce at this point another important term and concept, and that's an inversion. Now, the inversion that they show in your textbook is not a surface inversion. It's an inversion that's aloft. It's up in the air. What's the definition of an inversion? Well, that's if and when temperature increases with height. You see, it should be that temperature declines with height in the troposphere. But every once in a while, you can have a temperature increase with height for a lot of different reasons. Well, in this case, they have a subsiding column of air, perhaps a high pressure system that's creating a layer of warm air. And so when you look at the lapse rate diagram, well, from the surface, it goes down as you would expect. But because of that subsidence inversion, it warms up before it starts going back down again. So if and when there's a temperature increase with height, that's termed an inversion. Well, why are they important? Well, why if you had a cool layer of air under a warmer layer of air, what would happen? Well, that inhibits convection. Warm air doesn't rise, and pollution doesn't get mixed out if there's that capping inversion. Here, I think I'll show another slide that's a little better than our textbook one. Let's have a look at this one. Okay. Now, we learned earlier that the lower atmosphere is warmed by the Earth's surface. You have warm air, and then it's cooler aloft, and it gets colder as you go up. That's the normal pattern. But if and when you have a temperature inversion, and this may have been caused by cold air drainage downslope and clear skies at night, you have a layer of cool air underneath warmer air. And so how does the warm air rise? Well, it doesn't. As the air down here is cool, hits that inversion layer, the cool air is at a different density. It's not going to rise. All right? And so what happens then is that pollution does not get dispersed. All right, so some pretty bad pollution episodes have occurred because there is a temperature inversion at the surface. And here's the textbook, they look at this smog event in Salt Lake City. See, though, a lot of places that are sunny in climate have these problems with smog building up, and very often have a temperature inversion overnight. Okay, there's a special focus box in your textbook about Los Angeles. Los Angeles has some of the worst quality air in the country, if not the world. The air pollution, the smog is very bad. Well, why is the air quality so bad? To have that bad of an air pollution, you have two factors. One, you have to have a large affluent population and everyone drives. You have to have a big source. That's one part of the equation. But another part of the equation is the atmosphere's ability to disperse that pollution. And the Los Angeles basin, physical geography has conspired against it to create inversion layers, and air pollution does not get dispersed there. Even the native peoples that lived in that area noticed that there would very often be a haze hanging over the region, a haze, smoke from wildfires and so forth. All right. Well, today it's a lot worse because then we have auto and air pollution mixed in there. All right. Well, what happens? Oh, you see Waldo here. You may have played some of the Where's Waldo books when you were younger, but in this case, Waldo is already found. What does he want you to do? Instead of finding Waldo, you're supposed to find the inversions in this figure. All right, now how many inversions can you find? All right, well, what are they showing here? Okay, well, let's see. The current off the coast of California is a cold water current. Air is chilled, so you get a layer of cool under warmer hemispheric air. And so that's one inversion. Also, Southern California sits under what's called a high pressure zone, subtropical high pressure zone with sinking air. And so you have an upper air inversion. And then also you have cold air drainage from the mountains. At night, the upslope areas are very cold, and the air slips down slope by gravity, collects in the valley, and so that's another inversion. Also, its climate, it's mostly clear in Los Angeles, and with sunny skies, it means that overnight, with clear skies, the Earth's radiation just zips out to space. Cloudy nights, clouds act like a blanket somewhat, and they trap the long wave heat energy of Earth. What's colder in the wintertime, a cloudy night or a starry night? Well, starry nights are going to be a lot colder. Well, overnight, with the clear skies, the ground cools off, cools off, cools off. It chills the air above it, and so you get a layer of cool air where the warmer air is aloft. That's another inversion. So what does that make? That makes 4 inversions in total. And so it helps explain the reason why the Los Angeles basin, with its big population, big automobile population, has some of the worst air quality in the country.